Hello everyone, welcome to webinar on design of flat slab building with drop panels and column capital using MIDAS Gen 2018 version 2.1. I'm Nivedita Khole, looking into the technical support in MIDAS IT. Let me start with the introduction to MIDAS Gen. MIDAS Gen is a one-stop solution for buildings and general structures. Today's webinar will be using MIDAS Gen program. Let us look into the applications of MIDAS Gen. Applications include buildings, in which we see here Burj Khalifa. Burj Khalifa is an application because they used or they switched over to MIDAS Gen because of column shortening analysis. MIDAS Gen is a pioneer in column shortening analysis. Other than that, we have Gangsa Twin Tower, Hanoi Landmark, Moscow City Palace, who have completely used MIDAS Gen program for analysis and design. Under the plant structures, we can create blast furnaces, shell type of structures, as well as industrial sheds using MIDAS Gen program. Under the spatial structures, we see the Beijing Olympic Stadium, very easily modeled and analyzed. Then we have World Cup stadiums, airports. These all applications, there are a few applications of the many applications that we have for MIDAS Gen program. Then specialty structures, which include an irregular geometry like we see over here of a CCTV headquarters. Then shell modeling of the stadium, as well as the museum over here is a shell model, and we have also complete solid modeling. So this temple over here is a masonry structure which was analyzed for stress checks, and this is a complete solid modeling. Other than these, other than the buildings, power plant structures, stadiums, airports, we can analyze and design hangars, pavilions, subway stations, transmission towers. In the transmission towers, I'd like to mention that in the next version we are going to have a wizard for the transmission towers to make it very easy for the engineers to create the entire analysis and design report for the transmission towers. Then further, cranes, pressure vessels, machine structures, underground structures, all general types of structures can be analyzed in MIDAS Gen program. When it comes to reliability of the software, we take pride in mentioning that out of 20 skyscrapers in the world, 5 have been analyzed and designed using MIDAS Gen. That takes us to the Kingdom Tower of Jeddah in Saudi Arabia. They have completely used MIDAS Gen as a primary software for the analysis as well as design. Now the reason why they went for the MIDAS Gen, basically the consultant was Thomson Tomasetti. They have used MIDAS Gen program because of 4 main reasons. One reason is because of the user interface of MIDAS Gen, which is very friendly and could save a huge time. The graphics of the software is very much easier and faster. Then further, the second reason was the column shortening analysis. Of course, for such a high-rise structures, column shortening analysis is required to be performed, and like I mentioned earlier, MIDAS Gen is fully capable of performing the column shortening analysis in a user-defined construction stages way. The third reason was MIDAS Gen has got a high speed, that is using the 64-bit solver speed. It can perform the analysis in a very short period of time, as well as we have got GPU accelerators that can increase the speed. The fourth reason is about the soil structure interaction. Now MIDAS is the only program that can have a tight integration between the structural software solution and the geotechnical software solution. Langen engineers, they are the geotechnical engineers for this project. They have used MIDAS GTS NX. So Thomson Tomasetti could easily interact with Langen engineers. They could send their model into geotechnical software and get the soil spring supports and stiffnesses and take it back into structural software. And hence analyze the entire structure very accurately. So in this webinar, we will be using MIDAS Gen 2018 version 2.1. We'll be creating a flat slab building structure of G+5. In flat slab, we will be modeling drop panels as well as column capital. And after the modeling, loading and performing analysis, we will see the ways to extract the flat slab design forces. Then flexural design of flat slab as per EC204 will be performed. Then we shall see two-way or punching shear check, and under slab serviceability check we will be performing cracked section analysis for long-term deflection check. So let us go to the demonstration part now. I'll open up MIDAS program. This is MIDAS software solution. Let me introduce you firstly to the user interface. X, Y is the horizontal plane and Z is the vertical axis. Then further, this is the ribbon menu, which is divided into different tabs, and all these tabs are arranged as per the work procedure. So we go from left to right, that is first 4 tabs for modeling. Then we apply the supports in the boundaries, then apply the loads, perform the analysis, check the results, and then perform the design. And lastly, in the tools, we can also generate dynamic reports. In this way, it's very easy for, it's important that the entire model is not missed out with anything. Now, the tools that you can see in the View tab, these are available as shortcuts over here. Then further, I would like to explain another works tree, which is a very important feature in MIDAS Gen user interface. Herein we can see everything that has been incorporated in the model in one glance. We can also use functions like selection, assigning, then activation. All these types of commands can be used in the workstream from the workstream menu itself. Then we have the message window, wherein we can see directly if any error or warnings are displayed while we are giving the command. Then it makes it easier for the engineers to quickly find out the reason. Alright, so I'll begin with the modeling. Now I'd like to also mention that in MIDAS Gen we can have 4 ways in which we can create the entire model. The firstly, wizards are there, wherein we can create beams, columns, frames, arches, plates, shells very easily. If you're used to defining line grids and then creating the model, then that is also available. We have CAD type of tools, wherein you can start from scratch by creating the nodes and elements. And lastly, we have got the importing tool, wherein the Revit or Tekla files can be converted into MIDAS Gen text file and can be imported over here. Then 2D, 3D DXF files, AutoCAD DXF files can be imported. SAP as well as STAT files can be imported directly in MIDAS Gen. In this webinar, I will be using AutoCAD DXF file, a 3D DXF file, to start with the model. The advantage over here is that we can select the layers and for different layers apply different properties and then directly create the entire structure. Right now I'll select just one layer, one centerline layer, and over here I will define the material and section properties. We can do this later as well after we are done creating the entire model, but however I'll be defining directly by clicking on this 3-dotted box, which takes us directly to that command. So the material definition, I'll add the European concrete material property. We have got other standards as well for concrete materials, like if you want to use American codes or British standards, or you want to use Indian standards or Euro codes. So all these Japanese, Chinese, Korean codes are available over here. And we have a huge database as well for every standard. So in the Eurocode, we are going to use C40. The properties of the concrete are displayed over here and we can modify them as well. I'll click on OK and then we'll go ahead to define the section properties. In this flat slab structure, we'll have periphery beams and columns. So we'll click on Add. Let us firstly define the column property. So I'll select the solid rectangle and name it as column. The column size is 400 mm by 400 mm. So I'm taking care over here of the unit. It's in meters, so 0.4. I'll click on apply and I'll create beams as well. The beam has height of 0.5 by 0.4 and I'll click on OK. So column and beam definition is completed. Next, I'll go to the thickness and in the thickness, I'll click on Add and provide the thickness of our slab, which is 200 mm. So 0.2 meters and OK and close. After we are done with the property definition, then we can provide a scale factor in case our DXF file is in mm but we are inputting over here in meters. So we can provide a scale factor 0.001. However, my DXF file is in meters, so I'll keep the scale factor as 1. Further, we can put this file, AutoCAD file, at a particular location. So you can you can have importing of this DXF file multiple times and at different locations. So I'll keep the origin point itself. And further, automatic merging of duplicate nodes and intersecting frame elements will be done. The slab is not over here because we are going to be using AutoMesh command to directly create the meshed slab. Okay, now before we go ahead and create the mesh slab, we will do some modifications. Like over here in the workstream menu, as you can see, the number of elements and the properties that we have defined are displayed. The material property has been already assigned to all the elements. The column property has also been assigned to all the elements. So we do not want actually this column property to be assigned to our periphery beams. As you can see, this beam section property is in blue color. It has not been assigned to any of the element. We can double click and check that. The point is that now we need to change the section property that has been assigned to the periphery beams as beam. So all we need to do is simply select all the beams. So I'm going to the front view and selecting the beams. Now once we select the elements, all we need to do is drag and drop the property that has been defined, and there you go. We are done with the assignment of the beam section property. So it's very easy using the workstream menu. Just select and drag and drop. The thickness has also not been assigned because there are no plate elements. Now before going to the AutoMesh and creating our meshed slab, we will firstly define the drop panels and column capital. Let me take you back to the presentation. So when we are creating drop panel in other softwares, it is a pretty tedious task where you firstly need to create the slab and then you need to select the slab area and then assign the drop properties like the thickness. But in MIDAS Gen, it has become much easier. Simply provide the dimensions of the drop panel, assign it to the column and perform the AutoMesh. The dimensions over here as well, you can see these are, and you can also give an angle so that it orients along with the column. Let us see that in MIDAS Gen program. In the drop panel, firstly I'll define the drop panel size. I'll name it as drop. We'll have the shape as a rectangular one. It's a square shape basically of 2 meters by 2 meters dimension, but as per the reference image we will be providing B1, B2, H1, H2 as 1. The thickness that I'll be providing for this drop is 0.45, and angle is not going to be taking place over here. And I'll click on OK and close. Further, we can go ahead now and assign this drop panel. To assign the drop panel, we can simply select the columns and click on apply. Now to select the columns, we can use the secondary menu, in which I have already opened up the workstream menu. So in the workstream menu, to select easily, I can simply double click on the column. The assignment of drop panel will be done by simply clicking on apply. Now to see this drop panel that has been assigned to the column, I can use this workstream, right click and say display. This will show the drop panel area or drop panel size. This is how we have firstly assigned the drop panel. Now before we go ahead and perform the auto mesh, we will also be using the column capital. Usually the size of the columns expand towards the slab. This can be, instead of like having just only the column to have different section property, we can also have a rigid zone for the increased size of the column. That's the column capital. This column capital, however, in this webinar we will be using as a rigid zone for our column section shape itself, the original section shape. So let me take you back to the presentation. In other software solutions, the rigid zone of the column is not considered, or we need to manually create this rigid zone, which is a very big effort because you need to select the master and the slave nodes one by one for every column. Instead, in MIDAS Gen, the column capital can be defined along with this rigid link. There is auto rigid link option, as you can see over here. So by using this auto rigid link, the program, after doing the auto mesh, automatically creates the rigid links. So if we give the size of the column capital similar to the one of the column shape, then we can see that the auto mesh is considering the size of the column capital. So again, the procedure is simple over here. Define the column capital size, assign to selected columns and perform auto mesh. Let us go to MIDAS Gen now and begin modeling of the column capital and the slab. Okay, so firstly we will define the column capital and I'll name it as capital. It can be applied at the top or bottom or at both locations of the column. Then by looking at this reference image, I'll provide the dimensions of 0.2 for B1, B2, H1, H2, and I'll check on this auto rigid link so that I have a rigid zone at the cross section of the column. I'll click on OK and close. Then we will define, we will assign this column capital to our columns. So here I click on assign column capital, and to select the similar columns I can either double click on this column, or if you have selected few columns, then you can just simply say select previous and select the same elements that you have already selected earlier in the earlier command. So I selected the columns now and then I click on apply. This column capital can also be visually seen or displayed onto our workspace. There you go. Now we are done with defining and assigning the drop panels and the column capital. Let us see how automatically the program is generating these drop panels as well as the rigid zones. For that, we will go ahead now to the AutoMesh command. AutoMesh command is the best feature in MIDAS. Unlike any other software, you will not find any mishaps in the meshing of the entire planar area. Also, we have got different methods in which the mesh can be generated. You do not need to create the planar element first and then mesh it, but you can use the nodes or line elements to create the entire slab with the mesh. Of course, we do have option wherein you can select the plate and further mesh it. In this webinar, we are going to be using line elements. To select the line elements lying in one plane, I can use a very good feature that is select by plane. Use XY plane, provide the Z coordinate, and then I have done the selection. After that, we will check on mesh inner domain for creating the rigid zone subdomains as well. And then further, we will provide a mesh size. Now this mesh size is recommended to be span by 10 to span by 20. So the span over here is 9 meters and divided by 20 comes to be 0.45. So I'll be providing 0.45 meters. Element type is our plate. Now plate is because it takes into consideration the in-plane as well as out-of-plane bending. So it's an element or a planar element having 6 degrees of freedom for every node. Material property was already defined. The thickness was also defined already, so they are taken over here, and then we can simply click on apply. After we click on apply, we can see over here at the bottom, this is easy dynamic rotation that I'm using by pressing on Control and the scroll button. So we can see over here that the drop panels are automatically generated. Let us also look at the rigid links that the software has automatically created. As you can see over here, right click, say display. These are the rigid links created automatically by the program. Now after we perform the mesh, usually we need to also take care of the local axis, plate local axis. In other programs, you will have to very carefully mesh the entire plate, or you need to select one by one the plate elements and provide it with local axis or change its local axis. However, in MIDAS Gen, this procedure is very simple. Let us firstly display. I'll undisplay the rigid links first and the drop panels and the capitals. Okay, so here we hit in the display. In the display, we'll go to elements and local axis. I'll click on OK. So in the top view, it will be better. As you can see over here, the mesh has not created the plate elements with same local axis because the mesh has oriented in some other direction, or the shapes have also changed. Now to orient all the local axis, the local axis of all the plate elements, then we have a command that is change parameters, in which there is element local axis, planar, coordinate. The x direction of every local plate element has to be aligned to the same direction as that of the global x direction. We can have our own other direction as well. We can use change and have another angle increment, or we can have a beta angle over here. Alright, so now we simply select our plate elements by using the works tree. I'm double clicking on plate elements and I click on apply. So after we click on apply, we can see over here that all the local axes have been oriented in the global x direction. So just by one click, we are done aligning the local axis of the plate elements as per the reinforcement arrangement. I'll undisplay the local axis now. Okay, now over here you might be wondering, we cannot see the drop panels from this view or the top view. So no worries, we have got option over here to display the thicknesses or display the elements by different thicknesses or sections. So just use a random color and there you go. So here now we can identify easily our drops, our columns, and the difference between the beams and column section properties. Alright, so we are done with our floor plan. Now what we can do is we can go to the structure, and in the structure, firstly let us go to the structure type. In the structure type, we have to take care that the structure type is a 3D, mass control parameter is lumped mass, and we are converting the sulfate into masses because we are going to perform the seismic analysis. So we need to check this on, and since we are applying the lateral loads in the x and y direction only, we will just convert the sulfate into masses in the x and y direction. Then for a better display, we can align the top of beam sections with the floor and the slabs as well with the floor. This is just for the display purpose. Further, let us create different floor height, or let us create the entire building by replicating our floor. We'll use building generation command for that purpose. We will have 4 numbers because since we already have 1 floor, so we'll have for the 4 floors, and the height is 3.5. We can have different heights, and we'll click on add. Now, unlike other softwares, we can select a certain portion of the structure and then replicate it. However, over here I'll be selecting all of the floor. Now over here we have the options to copy node attributes. We need to take care that even the rigid links are checked on, and then we'll click on apply. So in this way we are done creating our G+5 building geometry. After we are done with the building generation, we will be going back to control data and defining the stories. The story definition is automatic. The program will automatically detect all the levels, and after we click on OK, it will create the stories. Over here, the advantage is that the program will automatically not consider the rigid diaphragms because we have created the plate elements. You can consider the rigid diaphragms by simply changing this to consider. Further, the eccentricities for the wind and seismic are also automatically calculated over here. This was done while we were saying auto generation. Over here, the 5%, 15% of planned dimensions for seismic and wind eccentricities respectively was mentioned. Alright, so we're done with the story data and we'll click on close. Next, we will go ahead now. We're done with the structure tab. We're done with the, before we go ahead, I would like to also mention that we have got check duplicate elements command, which can automatically find the duplicates and delete them. Okay, I'll go to the node elements. We're done with this tab as well. And next is the properties. Now in the properties tab, we have already defined and assigned the material and the section properties as well as the thickness. But in case you want to consider the cracking of the sections or cracking of the slabs, then you can use the scale factors available in MIDAS. This is similar to stiffness modifiers. So if you want to provide a stiffness scale factor to the sections, you can click over here. This is a very easy way of defining the section stiffness scale factors. Simply select the column section properties and provide over here the scale factors. You can apply it for the torsional, or you can apply it for the flexural moment of inertia. So I'll provide it as 0.7 for the major and minor axis bending. And then for the beams, I'll make it as 0.35 and 0.35. This is as per the American standard. Alright, so we are done with providing the cracked section properties. Similarly, if you want to consider the cracking of the slab, then you can provide plate stiffness scale factors. So as per the American standards, the plate stiffness scale factors can be modified to 0.25. Basically, we are providing the change in the stiffness of the elements because we are considering the cracking. And when we provide 0.25 or 0.3, 0.7, then we are considering only 0.25 or 25% of the stiffness for the analysis, or 70% of the stiffness of the columns for the analysis, or 35% for the beams, like that. So now to provide the plate stiffness scale factors, we need to select the plates and then click on apply. We're done with providing the stiffness scale factors to our elements. So we're done with the properties. Other than that, we do have options of time dependent material properties in case you're going to incorporate the non-linearity of the materials with respect to time. Alright, now I'll go ahead with the boundaries. We are going to be defining fixed support to our structure. So we'll go to define supports. I'll check on D all and R all. This is for constraining all the translations. This is for constraining all the rotations. And then I'll select the bottom nodes and click on apply. So in the workstream menu over here, we can see that the supports have been assigned. It can be displayed as well. I'll then display these. Next, in MIDAS Gen, there are advantages like you can have surface spring supports for rough foundations and pile spring supports as well for pile foundation. We can have substructure modeled in MIDAS Gen program itself also. That's a very good advantage, so that the entire structure can be analyzed in one go. You do not need to model it again in any other softwares. Okay, so we will be going ahead now because the rigid links over here, these have been already assigned automatically by the program using the column capital function. So we're done with the boundary conditions and we'll move to the loads. In the loads, let me take you firstly to the presentation. We are going to be applying static load on our structure, which includes the sulfate, the pressure loads in which floor finish of 1 kN per meter square and live load of 2.5 kN per meter square will be used. We will be applying wind load in the X and Y direction as per Eurocode 1/4/2005 par. Then further we are going to be applying the seismic loads as per Eurocode 8 part 1 2004. So let us start applying these loads on our structure in MIDAS Gen now. In MIDAS Gen, other than the static loads, we do have dynamic loads, that is the response spectrum loads and time history loads that can be applied. We can have temperature loads as well as post-tensioning done for beams and slabs. Then construction stage analysis is available. For high-rise buildings, column shortening analysis does require the construction stages. Moving loads can also be applied in case of ramps or industrial sheds wherein crane loads are to be applied. The good part is the program will provide us with the location of the wheel, because of which maximum reaction or displacement or forces are obtained for any node or element. MIDAS Gen also has got heat of hydration analysis. We can model solid elements as let's say for matte foundation where mass concreting works is done. And then in case there is a lot of cracking taking place, then we can introduce pipe cooling system. Further, settlement loads are also applicable. Now we are going to be applying the static loads. So firstly, we will be defining the static load cases. Sulfate will be coming under the dead load type. Live load. Firstly we'll have superimposed dead load. Then we'll have live load. We'll have wind load in X direction. Then Y direction. We'll have earthquake load in X as well as in Y direction. The list need not be in this manner. You can have firstly the live loads, then the dead loads or the wind loads somewhere in between, and the earthquake loads defined. No issues with the manner. Alright, but the type is important because depending on this type, the load combinations can be automatically generated by the program. We are done with the static load cases definition. Now we'll be going from left to right. So firstly, we'll define the sulfate scale factor of -1 for the Z direction, which is vertically downwards. Sulfate has been assigned and we can see that in our workstream menu. Next, let us go to the loads to masses because we're going to be applying seismic loads. We are going to convert our loads that are applied for in the load case of sulfate, in the load case of superimposed dead load, and as per the code we need to consider at least 25% of the live load into masses. Let us apply the wind loads now. So wind load add. We'll be applying wind load as per Eurocode 1 2005. The load case name is WLX, so we are going to be applying the wind load in the X direction. Now we're going to be using the recommended national annex. Let us look at the wind load parameters that we are going to be defining or we are going to be providing over here. So I'll go back to the presentation. And over here we can see that the frictional coefficient is 0.01 for we're considering the concrete structure as a smooth surface. So as per the table 7.1, it's 0.01. Then the directional factor, seasonal factor are as per the expression 4.2, note 2 and 3 respectively. Turbulence factor is also 1 as per the clause 4.4. External pressure coefficient, this can be automatically calculated as per table 7.1, considering zone D and E for our rectangular structure. So this is going to be automatic. Then lack of correlation factor, this is also automatically taken from the clause 7.2.2, 0.3 note. And the structural factor, this can be also calculated by the program as per chapter 6. So let us go back to MIDAS. Alright, so over here we are going to provide the frictional factor as 0.01. We'll keep the basic wind velocity as 26, directional factor, seasonal factor, turbulence factor as 1. The building height is automatically taken by the program since we had done story definition. The external pressure coefficients, CPE, CPI, these will be automatic, windward as well as leeward. Then the lack of correlation factor will also be automatic. We will be seeing what is the factor taken by the program. Everything, MIDAS Gen is not a black box. We can see what all it has done even though it says automatic. Then the structural factor, CSCD, this can be we can provide it manually or this can be calculated by the program. So we click on this small 3-dotted box right over here And then all the parameters are here except for the natural frequency. So after you perform the eigenvalue analysis for the structure, you can understand what is the natural frequency. Now since I had already performed the eigenvalue analysis and I know what is the natural frequency for the x direction, I will provide over here the value as 0.6358. I'll click on calculate, and the structural factor that the program has calculated is 1.253, and I'll click on OK. Then further, to provide this wind load in x direction, we'll provide a scale factor. So this will be in the positive x direction 100%, so that will be 1, and for the y direction it will be 0. Now before performing the analysis, we can click on the wind load profile and see the story forces, story shear, and overturning moments. And since I said, like I said before, it's not a black box, we can make a wind load calculation sheet and see how the program has actually used the formulae from the codes and the parameters that we have provided. And like I said, the correlation factor, the lack of correlation factor we can see is taken as 0.85 rightly as per the code by the program. Alright, so we can get the calculation, wind load calculation, and put it into our reports. These graphs also can be taken into reports. Alright, so we'll click on apply. That was for the x direction. We change the load case to y and simply change the direction, scale factor, and click on OK. Oh, before that, also we need to make sure that the structural factor for the y direction is provided, and the along wind natural frequency for the y direction, this was different. So this one is 0.7953, and click on OK, and we get structural factor is 1.15, and then I'll click on OK and OK again. So we are done with the definition of wind load in x and y direction. Next we'll go for the seismic loads. Click on add, earthquake, this is recommended. We'll use the same ground type, spectrum type as 1. All the parameters will keep it as same. Now the fundamental period, this we can manually input or we can have it also calculated by the program. So all these formulae from the code are taken. The fundamental period, especially this one, is as per class 4.3.3.2.2.3, which is 0.075 times CT into h raised to 3 by 4 for the moment resisting RC structure that we have. So that is the second formula as we see over here, and I'll click on OK, and the fundamental periods will be calculated. Similar to wind loads, we are going to be applying the scale factor for the direction of the seismic loads, so x will be 1 and y will be 0. Accidental eccentricities can also be included in MIDAS Gen. As we saw in the story definition, the eccentricities were automatically calculated. Over here we are not going to be using them, so we'll just click on none. Before performing the analysis, like wind loads, we can also get seismic load profile, the story forces, story shear, as well as overturning moments. We can get the story shear right over here, and we can click on make seismic load calculation sheet to see the calculations done by the program. I'll click on apply and further create a load case for the y direction. The period is same, so all I need to do is change the scale factor. EQX and EQY is done. Next, we're going to be applying pressure load, that is the superimposed dead load and live load onto our plates. Now for doing that, either we can select load case separately, or we can use this load type which can club the load cases in one type. So I'll make one typical type and at once select the SIDL and live load and apply the load of -1 and minus 2.5 as mentioned in the presentation. Then at once I can apply these loads on our plate elements. All we need to do is simply select the plates, provide the local direction or the global direction. I'll provide global Z direction and click on apply. In this way, I've applied the same load on all the plates. However, we can select different domains and we can apply separately the pressure loads onto different elements. So it's just about selecting and assigning. So we are done applying the pressure load. Now we will go ahead in the analysis, and in the analysis we can perform P delta, buckling, eigenvalue analysis. There is heat of hydration, moving load, settlement, nonlinear, and so on. All these analyses are available. Then we can now go ahead and perform the analysis. In the message window, we can see how the analysis is being performed, and because we've got a 64-bit solver speed, the analysis time is very low. As you can see, it's 5.02 seconds. Our G+5 story with so many plate elements is completely done. Now let us go ahead to the results. In the results, the first thing we'll do is create load combinations. Load combinations can be automatically generated by the program. And we can see over here that there is add envelope, that is the envelopes can also be automatically created by the program. So we can simply click on concrete, select the Eurocode 2, the recommended one, and click on OK. So over here, as we can see, the envelope, concrete strength envelope and concrete serviceability envelopes using all the load combinations already generated by the program taken in the envelope. So we can see the maximum and minimum values accordingly. Now we are also going to be performing design of flat slabs. So we will be looking for the concrete design, and in the concrete design we will create different load combinations. The design code over here we will select as Eurocode 2. We have other design standards as well. As the Eurocodes are available, we have got American standards, British standards, we have got Indian standards, and Korean and Chinese and Japanese as well. Alright, so we are selecting Eurocode 2 and we'll click on OK. So we see over here the strength as well as serviceability load combinations are generated. The good part is we can see the description over here. We do not need to actually look into the load cases again and again and the factors provided, which we can see of course after clicking over here directly. So it's a very user-friendly interface that we can easily say yes, yeah, okay. Now I'll close this. And we will go ahead now to checking the reactions. We can get the reaction forces and moments on our workspace. We can simply select our maximum strength envelope and let's see the vertical reaction. We'll see the values. These are the values, and the red one shows that the maximum reaction has been obtained at this location. We can click over here on this three dotted box for every result and get our table, results in the form of tables. These tables can be further taken into Excel sheets, so we can export it to Excel. We can even select a portion, or we can select the entire table and right click and copy and paste it into Excel sheets. That was about the reactions. Let us look into the deformation of the entire structure. Let's see the displacement contour. The displacement is checked for serviceability, so we will use the maximum strength serviceability envelope, and we will get a deformed shape. We'll have a legend, we'll animate, and let's not see all the values because the deformation is for all the nodes. We can, however, look into the minimum or maximum value. Alright, so as we can see over here, the recording is completed, and we can click on save to save this as a .avi file format and use it into our presentations. I'll close this. I'll just display a top floor, and I'll go to the initial view. Alright, forces and play forces moments. Alright, so we will look into the average modal values, and we'll look into the MXX, that is moment about the Y direction, that is moment in the X direction. Alright, so we are going to be checking on the legend, and we'll click on apply. So as you can see over here, this is where the least moments, positive moments are taking place, and the negative moments are higher at the supports. Also, because of the rigid zone, there are no peaks that will be generated. Let us look at that. We can use cutting diagram. We can create cutting lines simply clicking on 2 points. I'll uncheck the hidden views so that we can see the plates. So over here we have got, we can create a line, add it. Let's create one more passing through the center and add, and I'll click on apply. So this is how we get the positive moments as well as the negative moments. These are at the bottom. We can reverse the graph to see the positive negative moments at the top. So we can see over here the supports maximum negative moments are taking place, and there is no peak as such generated because of the rigid zone that has been considered because of the column capital that we have assigned to our columns. We can get these results in the form of graph as well, which can further help us to get the design force results. Alright, this was about the moment in the XY as well as the torsional moment. Now, the design forces that MIDAS Gen uses for flexural design is the wood armor moments. Let us go back to the presentation and discuss about the wood armor moments in detail. We saw that we have taken the moments per unit width. We can take the moments per unit width of MXX, MYY and MXY. Now, in order to calculate the design forces in the reinforcement direction, the software has to take alpha and psi with respect to the local axis of the plate element, that is X and Y. So these are the reinforcement directions 1 and 2, and X and Y is the local axis. While defining the domain, we can provide a different angle to the reinforcements. If we do not have the different angles in the subdomain, then the angles, the alpha and beta, alpha and psi values are 0 and 90. So the program uses this alpha and psi values and then calculates the wood armor moments. So the wood armor moments, these are the equations for the calculation. All in all, wood armor moments are nothing but combination of flexural and torsional moments. That is, wood armor moment in X comprise of MXX and MXY, and wood armor moment in Y direction comprises of MYY and MXY. X is the direction 1 and Y is the direction 2. And this is for bottom and top rebars. So we can see these results in the program. Okay, I'll uncheck the wood. Let's keep it on, no problem. So the wood armor moments in this, we can use top direction 1, and we'll see that. Alright, so these are the wood armor moments that have been generated. This is for the top direction 1, so we see that we're going to have good amount of top steel taken by the program. and that too at the location of the drops. Alright, now let us go ahead to discuss about another strong feature in MIDAS gen to extract the design forces. Because over here, if you want to take the design forces, then from the cutting diagrams we need to multiply we need to find the area, and that will be per unit width, and then we need to find the design forces. Basically we need to do manual calculation. But in case you want to avoid that, then we can use the local direction force sum. Let us discuss some more about local direction force sum using the presentation slide. Local direction force sum provides internal forces on a selected plane in a plate or solid elements. The resultant forces and the acting point, they are calculated on the basis of the nodal forces included in the selected plane. Once a detailed analysis is carried out for a specific part of the structure, like this strip, this function can conveniently calculate the member forces for structural design. The first point that we will be selecting while we define this local direction would be the starting of the cutting line, and the second point would be the other point of the cutting line, and the third point will define the direction of the local axis and which side of the elements are going to be used for the summation. So that is about the local direction force sum. We will now look at the forces. For that, let us select a portion of the slab. For example, we are selecting, we'll select this entire portion with the drops and the slab, and we'll click on active. Alright, I'll go back to the, that's okay. So over here we will define the points, one point here, the other point here, and we'll define one point at this side, and we'll click on calculate. So we can see over here that the moment, if we need to know the flexural moment about z axis, local z axis, it's displayed right over here, mz, which is minus 8.9, but that is for the sulfate. Let us look into a load combination, let's say COCB1, and click on calculate. So we can see 20.33 is the moment generated. So these are all the forces and moments that can be provided by local direction force sum. Also, we can see that the moment in the y direction is shown. We can also create the lines. For example, if we want to know what is the moment at these locations. So here we go. Depending on the local axis, we can find out what is the output of the result. So the measure bending for this, in this case, is mx, so that is minus 3.79, and mz value is 13.32. This is about the y direction, and for the x direction it is minus 3.79. In this way we can create several cutting lines, and we can provide names to it and click on add. After we click on add, we can check on this particular line, and then we can click on table output so that we get the results for any load combination in the form of table, which can be further taken into your Excel sheets. This is how easily you can extract the design forces using local direction force sum function in MIDAS Gen program. If you wish to know more about local direction force sum, please write to us. Alright, so that was about local direction for sum. Now we'll go back to the program. We're done with the extraction of results. Next, let us go to the design. I'll activate previous so that the entire floor will be activated, which I had activated earlier. And I'll click on initial view with the extruded view. We'll go to the design. So in the design, in MIDAS Gen, we have steel design, reinforced concrete, steel reinforced concrete design, as well as aluminium design. Sorry, not aluminium, cold form design. In MIDAS design plus we have got aluminium design. Anyway, so we are going to be performing meshed design. Firstly, we select the design code. So we are going to be selecting National Annex recommended for the Eurocode. We have other codes as well for design, that is American Standard, British Standard, Indian Standards, and so on. But for mesh design, we have European and American Standard. Alright, so after this, we'll go ahead and modify the concrete material. We can have a different material property for the concrete, as well as we can assign over here the rebar property. So here I'll select EN04 itself, class B for main reinforcement and class A for sub reinforcement. And then I'll click on modify and close. We can provide manually also the yield stress values for concrete as well as steel reinforcement. After we are done with modifying the properties, then we'll go ahead for the meshed design. In the mesh design, if you remember in the results, the load combinations were automatically generated by the program. Now if we click over here on the let's firstly look at the slab wall load combinations. We can see that the program has automatically divided the strength load combination, serviceability, as well as the load combination for the deflection for the slab automatically. And if we click on any of these load combinations, at the bottom we can see the description. So this is very much easier for the engineer to identify what exactly the program is doing. And you can edit that as well. Similarly, for the serviceability load combination, the quasi-permanent has been selected. The load combination, we'll see that later. Firstly, we will go for the design criteria for rebars. In the design criteria for rebars, we can provide basic rebar for the slab. So let's say we are expecting the top for direction 1, the basic rebars to be greater. So I'll have P12 at 200, and for the direction 2 as well, P10 at P12 at 200 spacing. This is the basic rebar that we have set, and the program will provide us additional reinforcement beyond these basic rebars. If we want the program to provide us automatically all the rebars, then we can just uncheck this basic rebar and the program will tell us which reinforcement to be applied where. So in this way, the program not only provides us with the area of reinforcement, but also with the arrangement of reinforcement. So here we can provide the program the diameters that are available on site, because instead of making changes later on depending on the site conditions, we can actually tell the program that P12, P16 and P20 are only the diameters available. Even the spacings, as per our requirement, we can just keep it until 300 and click on OK. Then further we can provide the effective covers over here by ourselves. So we can provide the effective cover, let's say 0.26, the clear cover plus the half of the diameter of rebar in the X and Y direction, both in top and bottom. So this, if we keep it 0, the program can manually calculate, can automatically calculate. So after we are done with providing the criteria, we'll click on OK. and then we'll go ahead further and perform slab flexural design. We can select average nodal values to be taken into consideration and provide a width, like our drop panels are 2 meters width, so we want to know, we want to have a smooth transmission of the reinforcement arrangement for 2 meters wide. So we have provided 2 meters width, and then the top, we can see as a result the top reinforcement for the direction 1, and then after we click on apply, the program will perform design for all, as in it will perform design top, bottom, direction 1, direction 2 reinforcement. It will show us on our screen the reinforcement that has been applied in addition to the basic reinforcement that we have provided. So until the design is taking place, let us discuss about the flexural design as per Eurocode 2. So we have seen that the load combinations were automatically generated and the load combinations were distributed for strength, serviceability and deflection check. And we could also provide basic rebar for slab, mat and shell. And further in the flexural design, we will be getting reinforcement for the average nodal values, and instead of element we're going to be using the width of 2 meters, and the rebar arrangement will be provided apart from the basic reinforcement that we will be providing. So unlike any other software, MIDAS Gen is capable of performing the design in the same software where the model is created and analyzed. There is no need for the engineers to move to a subsidiary software and perform the preliminary operations and then perform the design. This makes MIDAS Gen user-friendly and fast in terms of iterations, if you have any. Apart from the basic rebars applied, let us now look at the reinforcements that has been provided by the program. So we can see over here in the legend, the top reinforcement was 12 at 200, but apart from that, wherever we have got red locations, those are the locations where additional 12 at 200 and 12 at 300 are required. You can see these are specifically at the drop panel zones. And other than that, 12 at 200 is sufficient for the rest of the location. We can also see the bottom reinforcement. So it's not like a black box wherein you can just get the design design procedure of the software, but we can get the design for each and every individual element. So we can get even along with the formulae how the program has performed the design. Alright, so now let us go ahead to the slab shear checking. In the slab shear checking, we are going to be performing punching shear check based on the force of the column, because this is as per the code. We have other option, that is stress-based analysis, stress-based punching shear check, and we can also check one-way shear with the help of a cutting line diagram. Cutting line. So if you want to make a cutting line, let's say along this area only, then you can click on add, and then you can just let's select only this particular story. And we'll click on apply. So the punching shear check has been performed, and we can get the legend. We can see over here that it is quite low, less than 1. We can see the values as well on our screen, and this is the punching, one-way shear check that the program has provided. Alright, so these are the values on our screen. We can see from the top view, we can see this is what we can use further in our reports. So MIDAS Gen is very useful in case of reports as well. As you can see that the reports are generated not only for the flexural design but also for the shear check, the one-way shear check as well. At the bottom we'll see for the one line, one-way shear check, design result data. Alright, so this was about the punching shear check. Let us discuss some more about this punching shear check through presentation. Like I explained, there are two methods, force-based method and stress-based method. So the force-based method is that is code-based punching shear check. Here the program takes the actual force in the column supporting the slab as the shear force, that is VED. And the basic control parameter is U1. It is taken at a distance of 2D from the face of column as specified by Eurocode. The shear resistance of the slab without the shear reinforcement will be provided at the basic control sections, and that will be given by this formula. The reinforcement ratio is assumed to be 0.2 because we are not having any shear reinforcement over there. So then it is further checked with the limits, and further we can shear stress limits, and then we can if the limits are satisfied, then no need to provide the shear reinforcement. If so, then the program will tell you that the shear reinforcement is required to be provided, and it will give us with the area of shear reinforcement. So in this way punching shear check can be performed. Now let us go back to MIDAS Gen and perform the next check, that is slab serviceability check. So the slab serviceability check that we are going to be performing will look into the deflection, even though we do have the stress checking for concrete as well as reinforcement. The compressive stress check for concrete and the tensile stress check for the reinforcement. The concrete cracking, wherein crack width, minimum area of steel, rebar spacing, rebar diameters will be provided as per the code by the program to us. In this webinar, we are going to be focusing on the deflection, the immediate deflection and the long-term deflection. This is uncracked. If you want to see the long-term uncracked deflection, check on creep. And then I'll just select these and I'll click on apply. So over here the slab serviceability check is being performed for the selected plate elements. Let us look into MIDAS more discussion on this serviceability check. Now earlier we had seen the serviceability load combination as per the exposure class table 4.1. The quasi-permanent load combination is being selected as CLCB32. Then further we can apply the deflection limit. We have got serviceability parameters, so we can apply our manually different quasi-permanent deflection control limits, or we can go as per the code. So as per clause 7.4.1 part 4 of European code, we need to apply L by 250. So if we do not use this command, then automatically this L by 250 is applied by default. Okay, so I've actually stopped the check right now in between because of short period of time. This is the deflection, and we can get the design result of the short-term deflection or long-term deflection uncracked. Now we will look into the next part, that is the cracked section analysis in MIDAS Gen. So what I mean to say is MIDAS Gen is capable of performing cracked section analysis and then provide us with the cracked deflection. And also the program provides us with the crack points. So let us see this in MIDAS Gen program. For performing the cracked section analysis, it is important that the rebars are assigned to the elements. So here we go, we're going to simply perform the cracked section analysis. Over here in the message window, we can see that the analysis is being taken place. Let us discuss more about the cracked section analysis. Members which are expected to crack, they may not be fully cracked. They will behave in a manner intermediate between the uncracked and fully cracked conditions. And for these members, mainly subjected to flexure, as in the slabs, an adequate prediction of behavior is given by this following expression in the subclause of 7.4.3.3 in EN 1992, Part 4, 2004. Following factors, these are the factors that are going to be included, that is the effective second moment of area by the model, by elements for each iteration step. And we can see all this in the file generated as file names, that is whatever we have given a name to the file, _CSA.out. So we can see over here the actual tensile strength of concrete. All these values will be calculated by the program internally and will be shown in this output file. So our analysis has been performed. Now let's go to the cracked and the crack points, and we'll click on apply. So over here, cracking is not taking place because our deflection is well within limits. So we can see that in the design result that can be generated by the program. So the program is not, like I said earlier, it's not a black box. We can see how it is performing the checks. All the reports are automatically generated by the program itself. I'll select a portion, let's say for example this much portion, and then I'll click on design result so that we can quickly generate the design result. Right, so over here we can see that the deflection limit is fine. It is well within the limits, so it's okay. We can see the crack moment of inertia values as well that has been calculated. Now these values are too small, so they are 0. We can change the units to kilonewton as Newton mm, and then we can see further the results at any point of time. So this was about the results. Now let me show you in the presentation itself that the effective moment of inertia, the crack moment of inertia, the crack moments, all these values that are performed in every iteration for every node number, for every element number, can be provided by the program in this _CSA.out file. This is how we can get the result. As well as the provides us with a report. Alright, so if you have any questions, please write at the questions box. I've seen a lot of queries are here. But because we're running short of time, I request all of you to please write your queries over here itself, or you can write to us at shishir@midasit.com. The email address is right over here. Please write to us your queries and we'll be providing you with the right solutions. So we will be sending with all the queries and the solutions. Alright, thank you very much for your valuable time. We will be seeing you all again for further webinars. We'll be providing you with more notifications on our future sessions as well. Alright, thank you very much. We'll be ending the session now, so have a great day.